Hello and welcome to this lecture on fundamentals of AR VR XR systems. In today's lecture, we will continue the journey from the previous lecture and we will take a look at some new aspects such as tracking, sensing, interaction and system integration. So, to begin I would like to ask you a question. In a virtual world, how does a virtual object remain fixed on a real table even when you move around it? So, let us say there is a virtual object that has been placed on the real table and you put on your headset and you are moving around that virtual object, but it stays fixed on the table because it is not moving, you are moving. So, how do we ensure that this happens? Because indeed it is a virtual object. So, would not it also move along with you moving? So, how does it stay fixed and reflect the fact that it is only you in motion and that object is actually stationary? So, this is all dependent on accurate sensing, tracking and interaction, okay, and that is what leads to a sense of immersion in such XR environments. So, we will learn how this occurs in today's lecture. We will understand tracking in XR. So, at the end of today's lecture, you will be able to explain tracking. We will learn to differentiate 3 degree of freedom and 6 degree of freedom systems. We will talk about sensing technologies. We will understand about various interaction techniques. We will talk about the concept of sensor fusion and system integration, and we will also briefly appreciate emerging AI enabled XR systems. So, firstly the question why tracking matters. Imagine that there is a virtual chair floating in your room. So, as you move, the chair should remain stationary, as I was just saying. The perspective should change naturally and your distance should update continuously. Without this kind of tracking, the virtual objects will tend to drift, your sense of presence in the environment will collapse and the AR environment will become unusable. So, indeed the key insight from this example is that tracking is the backbone of XR and we need to ensure that. Let us understand what tracking is. So, tracking is a continuous estimation of 3 things: position or where am I, orientation or which direction am I facing, and motion or how am I moving. What tracking does is that it enables the system to maintain a consistent spatial relationship between the user and the virtual world, where you are and where the virtual world which you are experiencing is. So, the spatial relationship has to be consistent for you to feel immersed. So, let us say I have moved my body by 30 degrees, but the display does not update to show me what was at 30 degrees, what I would be seeing at 30 degrees. Then I will sense a loss of presence in the virtual world. So, a key concept in tracking is that of the degrees of freedom. A degree of freedom represents an independent way in which an object can move. So, XR systems typically use 2 systems for degrees of freedom. One is a 3 degree of freedom system and the other is a 6 degree of freedom system. In a 3 degree of freedom XR system, you only track rotation. In a 6 degree of freedom system, you track both the rotation as well as the translation. First, let us understand 3 degrees of freedom. This will typically consist of 3 rotational movements that need to be tracked: the pitch, which is looking up and down, the yaw, which is turning left and right, and roll, which is tilting the head sideways. So, this is rolling the head. So, you can think of it as rotation about 3 perpendicular axes x, y and z. So, the pitch which is looking up and down, yaw which is turning left and right, and roll which is tilting sideways. So, this kind of 3 degree of freedom tracking is used in the Google Cardboard and early Gear VR systems. The advantages of such a tracking is that it requires simpler hardware and lower cost, but the limitations are that it cannot detect physical movement through space. Now, let us understand 6 degree of freedom systems. These will usually track not just the roll, pitch and yaw, but also your x, y and z movement. So, if I move in the x axis or in the y axis or in the z axis, that will also be tracked. Examples of such systems are the Quest 3, Vision Pro and HoloLens. So, they are all 6 degree of freedom modern VR systems. These can give you room scale experiences, it can enable natural navigation, it can also give you a higher sense of presence. For effective tracking, we must ensure that the tracking is accurate, that is the positional error in tracking must be low, it must be fast, that is the latency must be minimal, it must be stable, that is there must be no jitter that you experience, and it must be robust, which is that it should be able to work in changing environments. Failure in any of these 4 dimensions will reduce your immersion, be it accuracy, be it the speed, be it the stability, or be it the robustness. So, we need a variety of sensors to carry out tracking. These include cameras, you may use accelerometers to track the acceleration, gyroscopes, magnetometers, depth sensors, GPS for location, microphones for your voice and eye trackers for your gaze or where you are looking at. So, these are the typical sensors that are used in XR. Let us talk about one in particular, it is called the inertial measurement unit or IMU, usually a part of your measurement of acceleration, rotation and orientation. Usually every modern XR headset contains an IMU. This usually has 3 components, the accelerometer, the gyroscope and the magnetometer. The accelerometer measures your linear acceleration, the gyroscope measures your rotational motion and your magnetometer measures your orientation relative to Earth's magnetic field. IMUs will usually provide very fast motion estimates. There are some advantages to such IMUs. These usually have high update rates, low cost and small size, but they tend to drift over time and as a result there might be some accumulated error. So, they are rarely used alone. So, in addition to IMUs, you may have optical tracking. This will typically use cameras to observe where the headset is, where the controllers are, where your hands are and how your environment is looking like. So, with the cameras you can see where the headset is located, where your controllers are, where your hands are and where the environment around you is and what it contains. The benefits of such optical tracking are that they are usually highly accurate and they use absolute positioning. Key challenges include that they are dependent on lighting and occlusion. So, if there is an issue with the lighting, then the optical tracking will be low. So, for instance, in low light conditions, optical tracking can be difficult, and if there are objects in the field of view or in the path of the camera's line of sight, then there might be occlusion of objects that are behind the object that is occluding your view. Typically, 2 types of tracking systems are present in XR systems. One is known as outside in tracking, where the cameras are located externally to the users. Okay. Here is your user and the cameras are external. Okay. This was used in early HTC Vive lighthouse systems. These of course, have high accuracy because you have 4 cameras tracking the person, but they are difficult to set up and offer you limited mobility. You may also have inside out tracking. Here the cameras are mounted on the headset. Examples are the Quest 3 and the Vision Pro. The advantages of these are that they are portable and they are easy to set up. Key challenges include that they are dependent on the environment and the processing of the data is computationally more complex. However, today this is the dominant approach, typically giving you the advantages that you can move around with the VR headset with the cameras on it, whereas in the outside in tracking you would need to set up the camera system to enjoy the VR environment. You may also use marker based tracking that uses artificial visual markers as shown on the right. So, this is from the AR toolkit, this is known as the AR tag, this is from the April tag and this is the Aruco marker system. So, these are commonly used in computer vision and have been leveraged for XR as well. So, you may use QR codes or AR markers as shown here to carry out marker based tracking. You place these markers on various objects and by looking at the markers you can tell which particular coordinate it is in the field of view. or what location it is in the field of view. Advantages of such marker based tracking are that they are simple and reliable, and they are used extensively in education and industrial AR. Often you use markerless tracking. This tracks the features in the natural environment rather than specific markers which you have placed artificially on the environment. So, for instance, you may use the corners of a room or edges or some specific textures to carry out tracking of objects. This gives you greater flexibility and much better user experience, and you do not need to set up these markers all over the place to be able to track. And indeed, as such they are the foundations of modern AR platforms. A key concept is that of simultaneous localization mapping or SLAM. We briefly talked about it in our overview and history of AR VR systems. It is one of the most important XR technologies. Here a system simultaneously builds a map and determines its location within that map. So, how that is done is using sensors such as LiDAR standing for light detection and ranging. So, LiDAR typically spins around and scans the world around you using some laser beam, and depending on the reflected light you are able to create a point cloud of the world around you, and using that point cloud you are able to localize yourself within that environment. So, you capture your camera images, you detect features on these images, then you track these features, that gives you an estimate of the position, and you update the map with your continuous location. You repeat this continuously, these 5 steps, to carry out your SLAM. So, modern XR systems require an understanding of your environment, and typically that is through floors, walls, tables, furniture and people. So, by gathering this kind of an environmental understanding, you are able to enable virtual objects to interact realistically with physical environments. If you have an understanding of the floor, the wall, the tables, the furniture and the people, accordingly you can set up your interaction that the user has with these sorts of objects in your area of influence. XR systems require you to fuse the data from multiple sensors simultaneously, and as no single sensor is perfect, we need to gather and combine information from sensors such as the IMUs, cameras, depth sensors, GPS, and by combining all of this information you can get improved estimates for where the user is, what is his motion, what is his orientation and so on and so forth. This process is also known as sensor fusion. Now, sensor fusion matters a lot in XR. For instance, let us say for some reason your camera is losing your visibility about where you are located in your current space. So, in such a situation the IMU continues estimating your movement when the camera has lost the visibility. So, because we are fusing the data, even if one of the sensor fails, we are able to take data from other sensors to update our location. So, that results in smooth tracking. So, sensor fusion is important because it increases the accuracy of your tracking, the stability and the reliability. However, tracking alone is insufficient. So, tracking is insufficient to give you an immersive experience. You must also have interaction in XR. So, interaction in XR is crucial to give you an immersive experience. So, interaction helps you answer various questions. The 2 top questions that interaction helps you answer are that, well, how do users communicate their intentions? So, because users may have some intention in the world that they are spaced in. For instance, they might want to go from one gallery in a museum to another gallery. How do they communicate that intention? And how do systems respond to the intention of the user? For instance, the user may want to navigate to lakeside in a park. How does the system respond and take that user to the lakeside? So, there are various interaction modalities typically used to enable user interaction in an XR environment. These include controllers, hand tracking, eye tracking, voice, full body tracking and also your biosignals. So, various modalities are used for interactions. These include controllers. You may press some buttons on your controllers and that helps you interact with your display. Your hands may be tracked and you may show some gestures. Your eyes may be tracked to show the intent where you are headed towards or what you are looking at. You may speak and your speech may be tracked to give an interaction with the system. Your entire body may also be tracked, or the signals such as your heart rate, your stress signals, etc., may also be tracked. Each modality of interaction offers some unique advantages, and we take advantage of these unique interaction modalities to give you an immersive experience. First, let us look at controller based interaction. It is the most mature approach and it is very often used. Two common examples are controllers used in the Quest and the PlayStation VR. These kind of controllers offer you precise way of collecting interaction from the users. They may also give you tactile feedback in the form of vibration. But of course, this is not how we interact in the real world. So, it will seem very artificial or much less natural than the real world. Next, you may have hand tracking. Hand tracking allows users to interact naturally using your hands, just like you do in the real world. Examples could be creating gestures such as pinch, grab or point. So, these are typical examples of how you track the hands. Applications of hand tracking include visualizing medical data, reviewing designs and for purposes of education. For instance, if you are looking at an X-ray image in XR, so you may be able to point at certain features that you see on the image. Or if you are reviewing a design, you might be able to collaborate with others where you are saying, oh, this surface on the car should look like this rather than be something like this. So, they are useful for carrying out design reviews and for purposes of education. Key challenges in hand tracking include occlusion and ambiguity in gestures. So, you might be thinking of something and showing a particular gesture, but that is not what might be interpreted by the system. And sometimes your hands may be occluded with objects in front. So, in that case also your hand tracking data will not be captured. Another key method of tracking is that of eye tracking. Here you track the gaze direction of the user. That is helpful in creating foveated rendering, where there is more detail in the center of your field of view and less detail in your peripheral view. Eye tracking is also helpful in analyzing the attention of the users and accordingly showing them the display as they would like to see. It is also helpful in making these XR systems more accessible in terms of users who may have special needs about where they are looking at because of maybe impaired vision. And also eye tracking can be helpful in predicting the intent of your user. Let us say I am looking at a specific app within my display, then that is the one that maybe needs to be magnified. So, eye tracking is increasingly important. They are not present in many headsets, many head mounted displays, and so they are being used for the next generation of XR systems. You can see an example of an eye tracker being used on a user who needs to put on this particular head strap that is able to track her gaze. You may also have voice interaction. Voice interaction gives you the benefits of hands free operation and natural communication. So, this has lot of applications in, let us say, virtual assistants or clinical simulations or for maintenance support. So, virtual assistants may use voice to interact with a user. You may also use them in simulations of in clinical scenarios in operation theaters, etc., where the interaction needs to be really fast, or for instance providing support for maintenance of machines. The issue with voice interaction is that it creates additional noise and also it may create concerns surrounding privacy of people. Another key interaction modality is that of haptic interaction. Here you may provide tactile feedback to your user. So, with let us say some vibration motors. So, examples of haptic interaction include vibration, force feedback and the use of haptic gloves. It improves realism and your task performance in general. You may also have full body tracking. In full body tracking, you capture the posture, movement and the gestures of the individual. So, here is an example of a full body suit, the Moxie mocap suit V100, and you can see there are these straps and it goes all of the way through the entire body of the person. This is helpful in sports training, in rehabilitating people, in for instance dance learning and in clinical assessment. Next, we come to spatial user interfaces. We know that traditional interfaces that we use in our computers, in our laptops, in our tablets and smartphones consists of windows, menus and icons, but XR interfaces have something more. They may have objects which are placed in 3-dimensional space. So, what we need are spatial user interfaces and not just a 2D interface as in your laptops, desktop PCs, smartphones, etc. Examples of spatial user interfaces include dashboards that may be floating in 3D space, virtual monitors or control panels. For instance, if you think about the VR Patients app which is available on Steam, that will usually have virtual monitors placed next to the patient, and the training doctor or nurse comes into this virtual environment and he sees a patient who has a particular medical condition, and there might be some monitors next to him which are showing the heart rate, the pulse and so on and so forth. And with the help of this kind of monitoring, the trainee doctor is able to take decisions on monitoring, assessment and treatment. Another key concept is that of social XR, where multiple users may share a common virtual space. So, these are increasingly becoming popular. So, we move away from let us say our normal video conferencing software such as Zoom and Microsoft Teams into interacting in 3D virtual spaces where we put on a headset and we sense that we are in a meeting room or a boardroom with people around us. So, that can help in various areas such as collaborative design, where people can come in and design together, remote education where you may feel that you are in a real classroom by putting on VR headset. You may be able to conduct virtual meetings, may be able to also perform telemedicine, where a person located in a remote area is getting diagnosed and treated by a doctor who is several hundreds or thousands of kilometers away. The key challenge in social XR is that you need to maintain that social presence continuously, and that is not easy. Another key area of interest in AR, VR, XR systems is that of digital humans and avatars. Here you can see an example of a digital human which has been drawn on a software such as Unreal Engine. Users increasingly interact with such virtual humans instead of real humans, AI agents and digital assistants. Typical characteristics of such virtual or digital humans and avatars are that they will be very photorealistic to normal humans and have facial expressions, speech, gestures and a personality of their own. Indeed, this is an important emerging research area where there is much work to be done, and those of you who are keen on this area have plenty to work on in the coming years and decades. So, key application area of modern AR VR systems is that of clinical extended reality in the field of healthcare. So, there are different kinds of use cases that people have found for XR systems in healthcare. These include virtual patients, clinical avatars and smart robo patients. Virtual patients are AI driven conversational patients. So, these use an AI engine to have a conversation with you, and what you say is passed using natural language processing, and the AI engine is then able to respond to what you have said, and what you are interacting with is often an avatar of this virtual conversational chatbot. We also have applications in clinical avatars where there are digital representations of patients which can help a doctor diagnose and treat a patient. Increasingly, smart robo patients are also becoming popular, where there are physical mannequins which are augmented with extended reality. So, there is a physical mannequin, but then it is also augmented with XR. Key applications of such clinical XR systems include medical training, improvement in communication skills of doctors, nurses, etc., healthcare personnel, and simulations of emergencies where people can be trained to deal with emergencies. Increasingly, networking and cloud XR are becoming quite important. XR experiences often require shared environments, interactions between multiple players or remote collaboration, and this is enabled by cloud computing. Often cloud computing is used to provide scalability, data that can be shared and rendering remotely. So, for instance, if you are playing a VR game, which is a first person shooter game, there might be multiple players from all over the world, and each player will have their own view when they are playing this game, and all of these need to be rendered simultaneously. And as the players make their actions in real world, there might be 150 players playing this one FPS game, and they might all be shooting at each other, and indeed at various stages various actions will be taking place in the real world, which need to be updated simultaneously according to the view that each user has, and that is not easy, and that is made possible by having a shared data space which is provided for by cloud computing. Now, sometimes cloud servers may be far away and the rendering may not be so easy. So, what we may also need is edge computing. Edge computing will enable you to compute locally with the benefits of reduced latency, faster responses and a better user experience. These are critical for the XR deployments of the future. Increasingly, we are seeing the use of AI in XR as well. AI increasingly supports understanding scenes, recognizing gestures, recognizing voices, creating interfaces that adapt with time and intelligent avatars. So, indeed, by providing all of these supports for XR, which are important in modern XR apps for instance, XR and AI are rapidly converging and coming together. If we think of a complete XR system architecture, we have an user from whom we collect sensor data and fuse the data. We track the user constantly, and based on the tracking we use some logic which understands this tracking data and renders it using a rendering engine. In addition, there are AI services at hand which also understand the user actions and the intent and help create an integrated display. Sensors are a crucial part of this system architecture, and sensors are the one that are helping you carry out the tracking. And these sensors are connected to the user through the headset, and as they collect the data is sent into a tracking engine. The tracking engine fuses all of the sensor data next, and based on the fused sensor data you actually update the display for the user. A number of challenges remain in these XR systems, typically three categories: technical, human and social. Technical challenges include reducing the latency in these systems and making them more real time, improving on battery life requirements. So, to be able to use the XR systems for long periods of time, and reducing the computational load through efficient algorithms. Challenges remain in terms of ensuring comfort for the users, maintaining accessibility for a wide variety of users, and ensuring that the privacy of users is not violated. We also need to think about the ethics of these XR systems, as they are increasingly integrated with voice based systems and AI, and we also need to think about who owns the data that is coming out of these XR systems. To conclude, tracking is fundamental to immersion. We really need to track to give you an immersive experience. Modern XR relies on sensor fusion to give you good tracking. Interaction extends not just to controllers, but to various other modalities that we saw today, and AI is indeed transforming these XR systems as we move through this era of rapid XR explosion. A key takeaway from today's lecture is also that XR is finding increasingly a number of applications in the healthcare space, which is a major growth area of XR. Looking ahead, in the coming lecture, we will cover human perception and cognition in immersive environments. We will look at visual perception, spatial cognition, attention, memory, embodiment and presence as we move on, and how these influence your immersive experience design. This I thank you for your attention, and I look forward to seeing you in the next lecture.